Hi, I'm Abhishek Lolge. I'm an incoming MS student in the CS department, and this is my application video for Partition. Today we'll be studying two algorithms. First is the partitioning algorithm used in the quicksort algorithm, and second we'll analyze the randomized variant of quicksort, which is called as the randomized quicksort. So in quicksort, you are given a list of n numbers, and you have to return them in a sorted order. So the sorted order in this case will be 3, 4, 5, 6, 7, 9 and 11. So in quicksort, you select an element and step by step you place x, selected element x, in its ideal position in the sorted array. What does that mean? So let's say this is your desired sorted array. When you select that element x, you want to place it in such a position such that all these elements before x will be less than or equal to x. All these elements after x will be greater than or equal to x. So how do we go about selecting an x and placing it in its rightful position? So if you have a given unsorted array, you fix an element. Let's say this is the first element, x. Now you traverse through the remaining array one by one, and you'll encounter some elements which are greater than or equal to x or less than or equal to x. You want to attain a configuration like this. The elements, some elements encountered should be less than x, less than or equal to x. Other elements which are greater than or equal to x, and these are elements that you don't know because you haven't seen them yet. So this configuration is called an invariant. And you want to maintain this throughout the process, throughout the entire sorting process. So let's run this partitioning procedure on this given array. So let's say you select x as 5. This is called as the pivot element. Now you will take two indices I and j. The index I you will initialize to the position of the pivot here, and you will initialize j after the pivot, which is here. Now what you will do is you will increment j throughout the array, and you will compare each of the element with 5, and you will do some swapping to maintain this configuration. Now here, comparing 9 and 5, when you see that a number is greater than the pivot element, you do nothing, you just go ahead. So j is incremented. Now the element at j position is 11. Again, this is greater than 5, so you will increment. Now you notice that the number is 4, and this is less than 5. So now you have to enter this scenario and swap some elements to maintain this configuration. What you'll do is you'll swap 9 and 4. That is the number at the index I plus 1 and the current jth element. So you'll swap 9 and 4. The resulting configuration will be 5, 4, 11, 9, 7, 3 and 6. And you proceed ahead. So current element is 7 and it's greater than 5, so you'll go ahead. Now the current element is 3. Now again we have to swap. So we'll again swap the numbers at position I plus 1 and j. So the resulting configuration would be 5, 4, 3, 9, 7 and 11 and 6. Now at this point, again the number 6 is greater than 5, so you will do nothing. Now we notice that still 5 is not in the right place as it should be. So what you do is, you swap the pivot element at the end of all these steps with the current ith element. So the resulting configuration would be 3, 4, 5, 9, 7, 11 and 6. So you notice that 5 is in its rightful place. All these elements are less than or equal to 5. All these elements are greater than or equal to 5. So this is the first partitioning step. So we notice that the array is still not sorted. So what you do next is, you take these two subarrays and you perform the same procedure again. So in that case, you might pick 3 as the 3 as the pivot and 9 as the pivot. So this step is called as the divide step, and the procedure that you'll apply on these subarrays is called as the conquer step. So the conquer step will be performed recursively. So this algorithm is a divide and conquer algorithm. So let's look at how this algorithm performs. So we notice that we are running through the array and comparing elements with the current pivot element. So let's say you have the input list as sorted, and you want to sort this list. So let's see what the quicksort algorithm might do. So if you notice, in this case, quicksort will place 1. If you pick this as the pivot element and you go through the array, now all these elements are bigger than 1. So essentially nothing will happen because 1 is already in its rightful place. Then you will recursively perform partitioning on this array. Again, you will select 2 as the pivot. Again, 2 is in its rightful position, which is less than 3 and 4. So again, nothing will happen. This will go on, and essentially you will see that the number of comparisons is order of n square. So the worst case performance of quicksort is n square. So there is another variant of quicksort called as the randomized quicksort. So let's try to analyze what happens in the randomized quicksort. In the randomized quicksort, what we do is, instead of selecting first element as the pivot, we select that element randomly. So what we want to calculate is the number of comparisons that are happening in the entire algorithm. So for analyzing quicksort, for the sake of simplicity, assume that you want to sort the numbers between 1 to n. Now you want to find the expected number of comparisons in this randomized algorithm where you are selecting the pivot at random. So consider some elements from I to j such that I minus 1, j minus 1 up to j. So we want to calculate the number of comparisons between any random elements I and j. So we should notice two things. The elements which are outside the range I and j are immaterial. So I and j will only be performed when either of these elements will be selected as the pivot. So if anything from I minus 1 to I plus 1 to j minus 1 is selected as the pivot, I and j will be separated like forever for the rest of the algorithm. So the only way I and j are compared is when I and j are selected as the pivot. So let C be the event where I and j are compared. As this event occurs only 2 times out of j minus I plus 1 times, the probability of C will be 2 upon j minus I plus 1. Now we will initialize an indicator random variable. Let's call it x. So we'll set x 1 when C occurs and set it 0 otherwise. So now we want to calculate the expected value of x. So the expected value of x, since it's an indicator random variable, the expected value of x will be just 2 upon j minus I plus 1. So since we are comparing, we want to find out when I and j are compared. Let's call this indicator random variable as xij for notational convenience. Now we want to find out these number of comparisons for all the elements in the array. That is, we want to find out the number of comparisons which is the summation of, this will be a double summation of xij, where I will go from 1 to n and j will go from I plus 1 to n. So I will go from 1 to n minus 1 according to this algorithm. Now let's try to bound this summation, which is equal to now if you let's try to set j minus 1 as k, j minus I as k. So this summation will be summation I goes from 1 to n minus 1, summation k goes from 1 to n minus I because of this substitution, 2 upon k plus 1. Now this summation might seem familiar because of this term. So this summation is equal to summation I goes from 1 to n minus 1 this is 2 times two times 1 by 2 plus 1 by 3 up to 1 upon n minus I plus 1. Now if you notice, this is a sort of incomplete harmonic series. Now this summation will be two times h of n minus 1 n minus I plus 1 minus 1 because 1 is missing in this bracket. Now where I goes from 1 to n minus 1. Now we know that the harmonic series is bounded by log n. So we could bound this bracket by log of n, which is equal to, which is less than two times log of n. And since the summation is going from 1 to n, we see that this entire term is 2 times n log n. So what we see that is the expected number of comparisons in a randomized quicksort setting is at the most twice n log n. So we see that randomized quicksort gives us an edge over the standard quicksort in that since it's a random we are selecting a random pivot, we are getting an expected number of comparisons which is less than compared to the classical quicksort algorithm. That's it. Thank you.